Okay, so our usual recap, let's see how much you remember. Define f prime for me.
It's function of x plus h.
No, what's the first part? Yeah?
When the limit approaches, when the limit approaches 0.
Limit as h approaches 0 up.
F of x, or f of x plus h. Minus f of x. Over.
What's the power rule? Tell me the power rule. Yeah?
It's n times x of n minus 1.
That's not the power rule, that's one side of the power rule. Yeah?
ddx.
The derivative with respect to x.
As, or x to the n equals nx and to the n minus 1.
That's the power rule. Remember, we want to memorize the entire rules. It's not good enough to memorize one side. I know you tell yourself that, yeah, I kind of know what's on the other side, but trust me, you will. When you're put under pressure, your brain doesn't think at that higher level of remembering that something was there when it's not there. So one reason why I do like you to remember, well, let me ask you this first. What's the derivative of ln x? 1 over x. So here's the thing. Every now and then I see students write rules on the top of their test. You know, you have these students who they just do this mind up because they don't want to forget it in the test and they just write down all the formulas. Every now and then I see them write down a formula, but they neglect to write down something like the ddx or something like that. Or they only write down one side of the rule. And then you kind of see them do these strange things in the test where they'll randomly replace an ln x with 1 over x for no reason. And the problem would, of course, be wrong. And then they would say, I don't know why I did that, right? So they would do something and they'll get to a point where the answer was ln2. And then they'd write down 1/2 for no reason, right? And what actually happened there is because you sort of equated in your mind ln x with 1 over x. When you become anxious and under pressure, you forget the fact that there should be a ddx in front of there. And you randomly think that ln of anything is somehow equivalent to 1 over the thing. And then when you come to me, you're like, I don't know what happened, Jhevon, because I know better than this. But the reason why something like that happens is because you are sloppy in memorizing your formulas. So memorize the entire rules when you're memorizing a rule to avoid things like that happening. It's very important. How do you differentiate e to the u? Yeah?
U to the, or the derivative of u times the u.
Okay. What does the product rule say? The product rule.
So would it be f times, or f of x times g of x? Okay, equals f prime times b plus g prime times f.
Is that right? DDX. We just mentioned that, right? You can't randomly replace the product of two functions with that expression. The derivative of the product. What about the quotient rule? So the derivative of something like f over g, what is that? Gerard.
So it's f prime times g minus g prime times f divided by g squared.
Okay, and remember the order matters here, so you can sort of save yourself by sort of memorizing the product rule and the quotient rule in the same order but changing the sign, or do your low d high d low thing. Whatever you want, but you need to remember that. What else what other rule do we have? The chain rule. Can someone say the chain rule? The chain rule is actually important for today's lesson. Chain rule. Tell me about the chain rule. What does that say? Yeah, Jimmy.
d over dx, f parentheses d of x. So the chain rule will be f derivative of g of x, derivative of g of x.
Right, today we're going to talk about implicit differentiation. That's going to be a very important component. Okay, so that's the chain rule. This tells us how to differentiate composite functions. Right, so if you have a function inside of a function, right, you know the basic rule, but you want to differentiate that sort of thing, you have to go through this process. Okay. Just making sure everyone remembers. Let's finish up the examples that we were doing last time and then we go into the lesson. So I believe in that list of problems we were doing, there were 3 left. One was, let's write them down. So this is problem 6. Derivative of x over e to the x cubed. 17. Derivative 2x plus 1 to the 8. X squared plus 1 to the 5th. Derivative we had an entire snow day to think about this, so. Okay, someone tell me how we do this.
Quotient rule.
Quotient rule. You can see that because we have a division of functions, and we can't really simplify. There's no real way to simplify this. Remember, we always try to simplify first, but you can't really do anything. So what does the quotient rule say? What would this mean?
Of like the function?
Yeah.
Okay, well, derivative of x is 1, so 1 times e to the x cubed minus 3x squared e to the x cubed times x.
Right, so it's the bottom times 0 at the top minus the top times 0 at the bottom. And here, of course, you're using that rule that the derivative of u is u prime e to the u divided by?
E to the x squared.
And you square that by. Which, remember, if you want to rewrite this without the parentheses, you'd write 2 times x cubed. Okay, simplify that a little bit for me.
You can take an e to the...
Okay, so in the top, e to the x cubed is a common term. What would we have left?
1 minus 3x squared times x.
Well, you can write 3x cubed at this point, right? And then we'll have this, which we'll be able to cancel this with that, because now we can cancel cross multiplication, and so that would be the answer. How do you do this one?
Product rule.
Product rule. Someone else walks me through this. We've been talking for a while. Okay, Juju, what do you get?
So we first find the derivative of 2x plus 1 to 8. So it will be a parentheses 2x plus 1 multiplied by the derivative of inside, which is 2.
You're missing something.
I said multiplied by 2, then times the x parentheses x.
No, you're still missing something.
Oh, 8 to the 7th power.
To the 7th power, okay.
Yeah. Multiplied by the g of x minus, plus, sorry. So the derivative 5 parentheses x squared plus 1 to the 4th times 2x multiply f of x.
Can you simplify that for me?
You can take
Right. The work we do here is going to be very useful for the next example, and then there's something else I want to learn about the next example. But yeah.
We can take out 7, 2x plus 1, and 4x squared plus 1.
Right. So to simplify something like that, we want to factor, which is a very typical thing to do, especially when you have fractions, because you want to factor so you can cancel stuff. So you want to start by looking for common terms. So, as you mentioned, 2x plus 1 is a common term. We also have x squared plus 1 is a common term. Any other common terms?
2.
The 2 itself is a common term. Anything else is a common? That's pretty much it, right? So we can factor out 2x plus 1. What power do we factor out for 2x plus 1?
7.
7. You always factor out the lowest power. What about the x squared plus 1? 4. 4, factor out the lowest power. Now you're right, what's left over? So what gets left over here?
44.
Well, there's the 8, we didn't do anything with that. We took this guy out, we took out the 2. there were 5 factors of this guy. We took out 4 factors, so we end up with just 1 factor left. Now you move on to the next one. The 5 we didn't do anything with, so he's there. The x squared plus 1 to the 4th, we took that out, so he's gone. The 2 we took out, but the x is left. There were 8 factors of 2x plus 1. We took out 7 of them, so there's 1 left over. And now we simplify what's inside the parentheses, right? So this is 2 times 2x plus 1 to the 7, x squared plus 1 to the 4th. Here you realize that this is 8x squared plus 8. This guy here is 10x squared plus 5x. Right? So what does that become now in the parentheses here?
2x squared plus 5x plus 8.
Everyone okay with that? Let's look at the last one. What would that look like? Yeah, John?
Well, it's the same, like, if you were to...
It's the same like this, right?
Yeah,
so we put a negative in the middle.
Right, yeah. It's like,
Right, so I chose these examples very suggestively, so once you did the hard work for number 17, you can kind of copy it for 18, because it'll look just like the product rule, except if we memorize in the certain order, except the middle sign will change, and that will be actually your numerator. So it's going to be the bottom times the derivative of the top, except here you have a minus the top times the derivative of the bottom. But now you have a division all over the bottom square. So this would be x squared plus 1 to the 10th. Now, this exact problem is not something you'd recognize, but you probably recognize something that looks familiar to this. On test 1, I think part B of problem 1, I gave you an expression like this to simplify. And it turns out how I actually came up with that expression was I took a quotient rule of something else. Right? So being able to actually do a quotient rule and then simplify afterwards is going to be very important for us. So these expressions will show up. So it's something you would need to know how to simplify. Right? But how do we simplify fractions? You go back to the strategy we talked about at the beginning. You factor the numerator and denominator and try to cancel stuff. And it's going to look very similar to this one. The difference is we changed the sign. So let's just use what we did already. This is 2 times 2x plus 1 to the 7 times x squared plus 1 to the 4th. Except here now we're going to have 8x squared plus 1 minus 5x. 2x plus 1. All over x squared plus 1 to the 10th. At this point now we can cancel this guy with some of those. So we have 2 times 2x plus 1 to the 7th. And here now we have 8x squared plus 8, but now we have minus 10x squared minus 5x. So this ends up being minus 2x squared minus 5x plus 8. All over x squared plus 1 to the 6th. Why being able to simplify is necessary is that at some point in the future, in certain contexts, we'll want to be able to set the derivative equal to 0. And in order to solve such an equation, you will need to factor. So simplification is important. So it's not something we did on a whim. Like, you need to know how to simplify stuff, how to factor things. It's going to be very important. Any questions before we move on? Okay, let's get to the meat of the matter, what we're actually here for today, which we should have started on Wednesday, but the weather did not want us to know the truth yet. So we're going to move on to 3.5, implicit differentiation. And they also cover log differentiation in this, logarithmic differentiation. And again, I was sort of sneaky because we actually did this in the class before, even though I didn't tell you that's what we were actually doing. Like when I proved to you the rule that the derivative of e to the u is u prime e to the u, I was actually using implicit differentiation. And when I actually proved the power rule for you, I was actually using log differentiation. So it is something we've seen before, and I think most of you are following, so it's not super complicated. This guy's mostly just an application of the chain rule, which I'll show you guys how that works. And then this is just using a log to simplify an expression, so it's easier to take derivatives, which something I tried to showcase in the last quiz, but I think a lot of you missed it. I saw Junji with his like super long quotient rule. I'm like, you use the log to simplify the expression. Why would you go back to the complicated expression?
I forgot to do the simplified version.
I'm like, okay, simplify the log of this thing. Hey, now take the derivative of the log of this thing. He just went back to the original. I feel like several people did that though. A lot of people I saw was like writing their answers into the other answers. I'm like, you're killing yourself. It's super easy. Use your answer to problem 3. Huh?
Is it correct though?
It'll be correct, but you spent a lot more time than you had to. And I don't know, you opened yourself up to a lot more room for error. So if you, I don't remember, did I post the quiz answers yet? Did I? Well, when you see the quiz answers, I scanned them, but I think I forgot to actually post it on the website. But when you see the answers, you realize how short the answer is. Anyway, so let's actually move on. What is implicit differentiation? Let's talk about this. Let's first introduce an idea. There are 2 ways we can actually define a function. There's the explicit way, and there's the implicit way. The explicit way is how you've always seen functions defined your whole life up until this point, right? So there's the explicit way of defining a single variable function. That's just to say that y equals f of x. This is called explicit because y is out in the open, y is by itself. It's right there, and it's explicitly this function of x. So we just see that that's the function, right? It's out in the open, it's explicit. There's also an implicit way to define a function. This is when it's not clear exactly what the y is, because the x's and y's are kind of mixed up together, right? So this would be something like if you see a function of x and y equals some constant. So example. Here are some explicit ways to define a function. Right, you can do y equals x squared. You can do y equals 2 over x plus 1. You can do y equals the square root of 2 minus x squared. The typical kind of stuff. Okay? What do I mean by something that's implicitly defined? This is when you encounter a function that is defined something like this. Notice that you don't have like the y on one side and only x's on the other side. The y's and the x's are kind of mixed together, right? Now sometimes you can solve for the y, but that's not how it's given to you. So like even like x times y equals 1, or 3x squared plus the radical of xy minus ln of y equals 2x. These are functions where that's implicitly defined. Right? That's what it means to be implicitly defined. Your x's and y's are kind of mixed up, right? And sometimes you're doing research or you're kind of trying to develop a function, and the rule comes to you in this form. It doesn't come to you in a nice form. It comes to you in a form that's all jumbled and messed up, But you still want to be able to do calculus. You still want to be able to find a derivative and do things with it, right? So we'd still want to be able to find y prime in this case, just as how we'd want to find y prime in this case, right? So now the question is, how do you actually go about doing that, right? If you don't know what the y is, how can you find a derivative? And how could it possibly make sense? What meaning would we give to it? That sort of thing. That is the goal of implicit differentiation. Sometimes you're given functions in a not nice form, where x is your independent variable and your dependent variable are kind of mixed together, but you still want to be able to do calculus. How do you go about doing it? The answer is an implicit differentiation. So whenever you have a function that's implicitly defined and you're trying to find the derivative, you say you're doing implicit differentiation. Everything we've been doing up until this point is explicit differentiation, right? But that's kind of the norm, so we never really mentioned it by name. But that's sort of the idea. So we can define functions implicitly, we can define functions explicitly. And the implicit way, it gives us a challenge. But, so the question is here, how would we find y prime? The answer, implicit differentiation. The main idea here is to apply the chain rule. There are other ways it's useful to think about it conceptually, but I'll sort of introduce those other ways when we're talking about related rates, which is a later topic we'll do. But for now, you can think of it as an application of the chain. We all know the chain rule. You guys told me what the chain rule was at the beginning of this class, so let's actually segue into this very carefully. Space on it. Because I want to do something and then I want to do it right below so that you guys can kind of match up. And then, oh, I see what's going on. Okay. Can I erase this? Okay. So here's the goal. I want you to find all the derivatives that I'm going to write on the board. Then I'm going to kind of express the function in a different way. And you're going to see how finding the derivative is hopefully kind of clear how you would actually do it. So now you just know your y is a function of x, right? So find all these derivatives. Right? Just find the derivative of f of x. What if I made it a little bit more complicated and asked you to find the derivative of f of x, and now I square the function? What if I ask you to find the derivative of something like x squared times that function squared? Or what if I ask you to find the derivative of x divided by some function? Tell me how you'd go about doing that. Right, so f of x it's some function, right? It could be whatever, but you don't really know what it is at the moment. Right? But you know it's some function. There's some expression with x's in it probably that happens in f of x. How would you go about finding the derivative? What's this one?
Replace f of x as u, so you'll get u. So you get u derivative. So f of x is f derivative of x. You replace f of x as u. Okay, and what would that do? Then you do the derivative for u. Then you find the
I'm asking you, how would you do that? What would you say the answer is here?
F derivative of
just that's almost like a definition. It's almost like a trick question. Okay, can't really do much there. But what about this one? Tell me how you would do it. What is the derivative here? Yeah.
So you have 2u. 2f of x multiplied by the derivative of f of x.
Okay, now you see what you just did? You applied the chain rule. There was no reason to name it something else. There was no point. You just realized that, hey, that is a composite function. That's something plugged inside a square function. So you apply the chain rule. What about this one? looks a little bit more complicated. What would you do here? How would you differentiate this? Junji?
So
let's call it Larry.
sure. So you use the product rule.
Product rule. We realize that there are two functions being multiplied by each other.
So
now I don't know the explicit definition of this function, but it doesn't matter. There are two functions being multiplied by each other, so the product rule applies. How would we apply
So
it?
you take the first derivative of the f of x, so 2x
So
by
differentiate this guy, leave this guy alone.
then plus take the differentiate.
Now we leave this guy. What's the derivative of this guy?
2 parentheses f of x times f derivative of x.
Yeah. Okay, that's just a chain. Okay, see? Junji's getting it. Someone else give me this one. How would you do that? John?
So you take the derivative of the x, which is 1,
Mhm.
and you multiply by f of x, subtract the minus x times f prime of x over f of x squared.
Okay, yeah. Guys did good. You applied the chain rule. So we understand the idea. Now, what often happens in math is that students get scared when things look a different way than they're used to. But that shouldn't scare you. The idea will be the same. Let me actually go through this again, but now I'm going to write things differently. Instead of writing f of x, I'm just going to write the letter y. Sort of take Junji's example of replacing it with a letter, right? So now if I ask you, what is that versus how would you differentiate this versus how would you differentiate this versus how would you differentiate this? What do you think the answer here would be?
dy dx.
dy dx. Or you can write that as y prime when your independent variable is understood. How would you differentiate this?
2y. dy dx.
2y
Y prime.
times the y prime, right? Why did you have to multiply by y prime? You're applying the chain rule. That y just represents a function. You don't know what the function is, but the chain rule would apply to that function. So once you differentiate a y with respect to x, you need to multiply by y prime because you're really applying the chain rule. What about this guy? How would this look? Tell me, what would we see?
2x times y squared
You have 2x times the y squared.
plus plus x squared times 2y times y.
Now I want you to realize what's happening here. It's not exactly correct to say this in general, but what you can see is happening here is you apply derivatives rules as usual. So if I see a multiplication of functions, I do have to go through the product rule. In this case, because I'm doing the derivative with respect to x, when I differentiate an x term, I don't do anything. But if I differentiate a y term, I have to multiply by y prime. Why? There's some function in there that I don't know about, but the chain rule would have to apply. Right? So whenever I differentiate a y term, I just multiply by y prime. Differentiate an x term, you don't do anything. Are you guys getting the idea? So if I ask you to differentiate this guy, how would you do that? Well, it's the same idea. You have one function divided by another function, so the quotient rule would apply. So you'd apply the quotient rule. What is the quotient rule? It's the bottom times the derivative of the top minus the top times the derivative of the bottom. So this is just why it represents a function. You just put the function prime divided by the function squared. It's no difference whether I wrote it as f of x or y. The same rule applies. Right? Y is just some function of x. I need to apply that chain rule. So how this actually happens when at the application level is whenever I differentiate a y term, multiply by y prime. If I differentiate an x term, don't do anything. Right? That's not the exact rule. We'll generalize it, especially when we come to something like related rates. That would not be enough to think about it that way, but it is enough to think about it that way here. That's the basic idea. Okay, so now we can talk about how we would differentiate an implicitly defined function. Now that we know how to differentiate these single terms, let's kind of put this all together. Can I get rid of this? So this is the goal for the next few problems. Find y prime, as in dy dx, as in x is my independent variable. That's the input, and my y will be considered the output. So let's say you have a function that you're given, and it's just x times y equals 1. That's the function. Find y prime. We're going to get a little bit more mileage out of this one because there's a possible way to do that explicitly as well, obviously, but we'll talk about that. Here's another situation, which I kind of made look hideous on purpose. 5x squared plus 2x I want you to find y prime from that expression. Also want you to find y prime in this expression. We have some more examples to go through, but I want to illustrate something with these examples. Right, so in the world of implicit differentiation, there are really three kinds of situations you can find something which are illustrated by these examples. But let's actually solve them first. How would you go about solving this one? Okay, so you want to just differentiate both sides of this equation. To differentiate this, you would use the product rule. Why? It's one function times another function. How would that be applied here? How do you apply the product rule?
It's y. Yeah.
So you differentiate this, so it's y, yeah?
Plus x y prime equals 1.
Derivative of 1?
0.
0. Okay. Now the goal was to find y prime, correct? How do we find y prime? I just have this.
Put all numbers.
Yeah, algebra is the answer. You're going to do a bunch of algebra and you're going to solve this equation for y prime. Get everything that doesn't have y prime on the other side. Notice here we have a multiplication, so we can divide both sides by x. Now there are some comments that I can make here. One, how do you know you can divide by x? What if x is 0? Is it possible for x to be 0?
No.
Why is it not possible? What's your answer?
So for x to be for the statement to be true, then the equal should not be 1. It should
Right,
be 0.
exactly. I know x is not 0 because x times y is 1. If x was 0, this would be 0. So I know it's okay to divide by x. So this kind of makes sense to me, right? On top of that, if it were the case that x could possibly be 0, you will just say the derivative is undefined there. And we'll talk about what it means. We already did talk about what it means for the derivative to be undefined, so that's cool. But that's not an issue here. Here's another thing about this example, though, that we can get some extra mileage out of it. So sure, I just taught you implicit differentiation, so it was kind of, that's your prime to think of it that way. But the thing is, you could also do it explicitly, couldn't you?
Wouldn't you just divide the x?
You could have just solved for the y in the first place. You know you can divide by x because x is not 0. And this is something you know how to do. How do you differentiate 1 over x?
Negative 1 over x squared. Yeah, negative 1 over x squared.
Right, you think of that as x to the minus 1, apply the power rule. So this would mean that your y prime is equal to minus x to the minus 2. Now let's look at this case. Here's an example where we could do it both implicitly and explicitly. Not all problems are like that. In fact, this one is not like that. This one's kind of like that, but you kind of wouldn't want to do that. But we have two different answers here. I want you to notice that in this one, there's a y in my answer. Right, so here the derivative is defined in terms of the dependent variable. Are these actually the same? These answers look pretty different to me.
You did write the same answer.
Are they the same? Well, they better be, right? We just found y prime in two different ways. How do we know that both answers make sense?
Plug in.
You can literally just plug in for y. In this case, you could have solved for y here, and you would plug in 1 over x, which gives you minus 1 over x squared. So the answers are actually equivalent. But this is a very nice example. Not every time you'll be able to do that. Let's move on to this example. So there are times when you can solve a problem both explicitly and implicitly. You just, okay, if you didn't give me in a nice form, put it in a nice form, and I can do it, right? But the answer that you get in either way, there will be equivalent in some way. But not all problems are so nice. What about this one? Could we actually do this explicitly? Could I solve for y here? Does anyone see how to solve for y? Yeah?
So we first divide by parentheses 5x squared plus 2x on each side. Then so we factor out y. So it will be y parentheses 1 plus x squared y parentheses equals to 4x squared. Then divide by 1 plus x. Sorry, my bad. X of 4 to the y.
That's not going to work. Let me write it in another suggestive way. What if I wrote it like this? Would you realize how to solve for y now? What do you notice about it? It's a quadratic, right? So we can actually use the quadratic formula. So it is possible to solve for y here. Take x, this to be the a, this to be the b, and bring that to the other side and call that the c. You could actually solve for that using the quadratic formula. Now the point is, that would actually be very ugly, right? Let me do it for you, right? I could think of this as x to the 4th y squared plus 5x squared plus 2xy minus 4x cubed equals 0. And so I can solve for y using the quadratic formula. It will be minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now here's the question. Would you want to differentiate something like that? No. So a lot of students might see problems like this and they're thinking, why do we need implicit differentiation, right? I don't want to learn this. I'll just solve for y every time and do that the way we've always done it. Here's one example of why you wouldn't want to do that. It gets even worse. In this one, it's literally impossible to solve for y. It's impossible. Because if you think of y as this variable that you want to solve for, this would be a 7th degree polynomial. You can actually mathematically prove that there is no general formula to solve polynomials that are higher than the 5th degree, right? So you might get lucky, but this is an example that I chose that does not have a solution. You cannot solve for y. So even if you wanted to do something like this, you can't do it. It's mathematically impossible for me to solve for y here. However, if this is a problem I need to solve and I want to use calculus on, I need to know how to get to the derivative somehow. And this is why implicit differentiation is important. Sure, sometimes you might not need it. Sure, sometimes you'd rather use it, but you can do without it. But there are cases where you don't have an option. You you need it, right? So implicit differentiation is an important thing. And it's a very useful tool because we use it to prove a lot of derivatives. So I'm sure you can imagine what it would be like doing the quotient rule on something like this. It's not going to be fun. But now with the power of implicit differentiation, it can be a lot less stressful. This problem is still going to be kind of annoying, but I really wanted to illustrate that. But now you can see, let's actually solve this using implicit differentiation. Let's get to y prime. What would that look like? How would you differentiate this first term? Product rule, because it's one function times another function. And I know that when I'm differentiating the y, that will just become y prime. So I'm going to differentiate the first one, leave the second one, plus leave the first one, differentiate the second one. Plus, I differentiate this term. It's again the product rule. Differentiate the first one, leave the second one, plus you leave the first one. What would the derivative of the second one? What's the derivative of y squared?
2y,
Yeah.
y prime.
2y, y prime. You need to remember to put that y prime there, the chain rule. The y is some function that you don't really know how to solve for. Equals, what's the derivative of this side?
12x.
Okay, so that was bad, but not so bad. It would be a lot more annoying to do the quotient rule. But now the goal is to do what? Solve for y prime. There's a y prime, there's a y prime. How do I get the y prime? Algebra. It's kind of like why we spent almost a month on algebra, right? It's going to come up. So, how would you solve something like that? Yeah, John?
You subtract the 10x plus 2 times y and
Yeah.
the...
All the guys that don't have the y prime, move them to the other side, right?
And then you,
So, yeah, so that would be just this guy.
no, this third one too. No, wait.
So on this side, we'd have the 12x squared minus the 10x plus 2 times y.
Should there be another? Oh yeah, the 4x to the third and the y squared.
And then the 4 to the third and the y squared. So that gets rid of these guys. What happens with what's left over?
You factor out the y prime.
Y prime is a common term. So you'd factor it out. I'd be left with 5x squared plus 2x plus 2x to the fourth y. And then just divide both sides by that.
Yeah.
Right, so obviously the derivative here has some issues. It will not be defined if this denominator is 0. But as long as we're not there, this is the derivative. So we found y prime. Slightly annoying, but I guarantee you it would not be as annoying as you applying the quotient rule to that thing we had before. You guys can do that for fun if you want and compare. We have a few minutes, let's do the other one. Next time we'll talk a little bit more about differentiation, how to make meaningful statements about an expression like this. Like if I were to ask you a question like, how do you find the tangent line? Which we know doing that is important. How would you go about finding the tangent line at a certain point if your derivative is a complicated expression like this? That we'll talk about next time as well. But let's just finish up the last of this example, this set of examples here. And we'll call it a day. So here's an example of something that you couldn't solve for y if you wanted to. It's also not a function, by the way. If you were to graph this, it would look something like this. So it won't even pass the vertical line test, which is the power of implicit differentiation also. It kind of works even when what we're looking at is not really a function. But let's continue. And there are tons of things, by the way, that are not functions, like circles. There are lots of times we want to deal with a circle, but a circle is not a function. Does calculus just not work now? No, we have to find ways around that. Okay, so derivative, find y prime. How do you go about it? How do you differentiate x squared? Plus?
Times negative, times y prime.
Times the y prime, right? Minus?
2y prime. Right.
2y prime. Whatever the derivative of that is, I don't know. It's just y prime. 3.
0.
Now for the quiz on Tuesday, I would give you a problem that's closer to this one than that one. I was just choosing an extreme example here. But yeah, so at this point, you want to solve for y prime. You identify all the terms that have the y primes in it. All the terms that don't have y primes in it, get them to the other side using the opposite operation. So then this here would come over here, do a minus 2x. And then on the left side, we'd be able to factor out the common term. And then I'd be able to divide. And that's your derivative as long as this denominator is not zero. Next time I'm going to ask you to find a tangent line to a point on this curve. And we'll also cover log differentiation and do some other stuff. We'll stop there.
That will look halfway right now.